2, motion of a falling object for physics 2211. Here are the things I'll be going over in today's video. Purpose of the lab is to observe and compare data of a free falling object model from rest to two computation model that differs in the presence or absence of force of drag. An object I use is crushed paper ball with mass of 0.0045 kilograms. Computational model with drag force was more similar with the observational model in terms of the slope, while computational model without drag force has a steeper slope. I used Newton's second law, gravitational force, and drag force in my lab. Newton's second law describes a change in the system's motion caused by some forces acting upon the system. If there is no net force, there will be no momentum, and thus we can constant velocity. We can derive the velocity and position update formula from Newton's second law. Gravitational force is simply just mass times gravity, with gravity being negative 9.8 meters per second squared. And drag force is here as listed, where b is a constant and v hat is a unit vector for v. Some initial conditions and assumptions include: for a model without drag, assume gravity is the only force acting upon the system. For a model with drag, there is a non-constant drag force in addition to gravity acting upon the system. Some initial conditions include: system is a ball only, surroundings are the hands, air, and the ground, and the ball is dropped with zero initial velocity. The procedures as follows. I recorded a video of me dropping a paper ball, and I used tracker to generate a position versus time graph of the paper ball, and then took the data points. I used Glowstrip to generate two different computational models, one without drag and one with drag. I input all three models' data point into Google Sheet and generate a graph that compares the positions of each model. Here's the observational model. System is a ball only, surroundings are the air and the earth, and the initial positions as listed. As you can see, the ball moves in the negative y direction as I'm dropping it. Computational model without drag is as the following code. B is 0 because we're not including the force of drag. And then since there's no drag force, the F net will just be force of gravity, which is mass times gravity. And I use the velocity and position update formula to update its respective graphs. Here is the model, but with drag the code is pretty similar except for a few changes. B value is now 0.005, and then now there's a new force of drag is equal to the following code. So then the F net will be equal to force of gravity plus force of drag. Observed model's motion is most similar to that of the computational model with drag force. Computational model without drag force has the greatest net force vector in the correction negative y direction. Therefore, its velocity increases at a faster rate. Resultant net force vector's magnitude of a computational model without drag is greater, since it did not take into account force of drag. Some potential errors include human errors, rounding error when inputting positions, assumption of system is a ball only, and the shape of the ball affects the b constant and drag force, since the ball is in perfect sphere. What does it mean? The computational model with drag force best predicts the terminal velocity, because since the velocity time graph plateaus, that means the drag force vector and gravitational vector will be close to the same magnitude, and then the net force will approach 0. Non-zero initial velocity will not result in a different terminal velocity. Terminal velocity can only be changed if the mass is changed. Having non-zero initial velocity will simply make the object reach terminal velocity quicker. Thank you.